Hello everybody. In this tutorial we're going to take a short look at SciKit Learn and why it is such a powerful tool. SciKit Learn is a machine learning framework which is built on top of libraries like NumPy, SciPy and Matplotlib. It allows us to use many different machine learning algorithms, and they are also easily exchangeable. So if we trained some model on a specific data set, we can easily swap this out and use another model and therefore test the performance of different model architectures on the same task without rewriting the whole code. In this first tutorial, we're gonna take a look at supervised learning with scikit-learn. And specifically, we're gonna take a look at regression tasks, classification tasks, and then we are gonna take a look at the model evaluation. So what possibilities we have to evaluate the performance of a model and maybe compare it to other models. So we take a look at good metrics to compare different models. After this short introduction, we get to our first example. So as I already mentioned, we want to talk about supervised learning today, and especially about regression in this example. So for regression is the process of fitting some model or function to given data points. And here we generate some synthetic data, and our data points are these 100 random points between 0 and 10. And then we have our targets, this epsilon, this y, and to get this y, we apply the function 2 times the data point plus 3 plus some random noise between 0 and 1. And yeah, now we want to train a model to understand this function we apply to the data points to get y. And in scikit-learn, we can just use the linear regression model. So we can import it from sklearn linear model, and we can simply create a new model with model equals linear regression, and then we have to train the model, and we can do this by calling the fit function, and we need to provide the data points which are stored in X, and we need our targets, this is the Y, and if we execute this, the model gets trained on this task. And yeah, then we want to make our predictions. So we call the predict function from the model again on our data points, and then we can execute. Then we have our predictions, and now to evaluate the model, we want to call the mean squared error. So we want to know how much the predicted data points vary from the actual targets y. And this is done by calculating the mean squared error from the data points and our predictions. And if we execute this, we can see we get a mean squared error of 0.83. And this is not super good, but not too bad. If we take a look at the data points, they are between 0 and 10. And we apply some random noise between 0 and 1. This is something the model can't really learn. So we would expect some error. And yeah, we would expect the error to be in the range of this random noise. So it performed pretty good. We can now also test this without the noise. So we just remove this random noise and then we execute it again. And then we can see the mean squared error is 4.4 times 10 to the power of minus 30. So it's very small, and there we can see this linear regression learned the task almost perfectly. And yeah, so if we don't apply the random noise, the model can perfectly learn the task. Then to our next task, and that's the so-called classification task. Classification is different to regression in terms of, for regression, we want to fit some curve to the given data points, like in the previous task. And for classification, we want to classify the data points to different classes. So, for example, for cars, we could build a classifier to classify each car to its brand, or yeah, there are many examples. For classification in SciKit Learn, we can see it looks very similar to the previous regression, and that's because we can also see here we use the logistic regression model, but that's just a naming scheme thing from sklearn. This regression model is meant for classification. I'm not totally sure why they named it like this, but this model is poorly used for classification. And yeah, it is very similar. We can see again, we have this logistic regression model we import from linear model. Then we just create a new logistic regression model. We again fit it to the data and can make predictions again. And yeah, the only thing that's really different here is that we use a dataset. That's the so-called Iris dataset. And yeah, we load the data and the targets here. Then we split the data in a test and train set. And yeah, so here you can see the test set is 20% of the whole data. And then we get this X train, X test. So 80% of the data is in X train, 20% of the data is in X test, and the same for the targets. So 80% is in Y train and 20% in Y test. Then it's important to only fit the model on the trainings data, and then we can call the predict function on the test data. That's nice because the model has never seen this test data. So if it gets a good score on the test data, we know that it generalized very good. And so generalization means it can make good predictions for data points it has never seen before. And if we execute this model, we can see we get an accuracy of 1.0, so 100%, and this is on the test data, so the model performs really good. And yeah, for the dataset we used, this Iris dataset contains information about different flowers. So if we take a look at Y, we can see we have here 3 different classes of flowers. And if we take a look at the trainings data, we can see we get a long array with different information for each flower. And these are the petal length and sepal length for the given flowers. And also it's the length and the width for the petal and the sepal. So yeah, this classifier can classify these 3 different flowers given on this data, and as we can see, it achieves accuracy of 100% with only this logistic regression model. So yeah, it's not too difficult to learn. Last chapter in this tutorial is model evaluation, and we already saw some different ways to evaluate the model performance. For the classification task, we had the accuracy, so the fraction of the correctly classified instances. For the regression task, we used the mean squared error, and yeah, we can see here some different metrics that can be used for classification tasks. So we have the precision, recall, and F1 score. They all are not perfect, but they have different strengths, and in the F1 score, the strength of the precision and recall are combined. And yeah, these different metrics can help us to show some specific strengths and weaknesses of different models, and they can help to compare these models. And for regression tasks, we can use something like accuracy, and we have to use something like the mean absolute error or the mean squared error, as we saw before.